Hi everyone, welcome to my audiobook. Today's lesson is from NCERT Chemistry, Part 1, Class 11, Unit 6, Equilibrium. So let's start. Chemical equilibria are important in numerous biological and environmental processes. For example, equilibria involving oxygen molecules and the protein hemoglobin play a crucial role in the transport and delivery of oxygen from our lungs to our muscles. Similar equilibria involving CO molecules and hemoglobin account for the toxicity of CO. When a liquid evaporates in a closed container, molecules with relatively higher kinetic energy escape the liquid surface into the vapor phase, and number of liquid molecules from the vapor phase strike the liquid surface and are retained in the liquid phase. It gives rise to a constant vapor pressure because of an equilibrium in which the number of molecules leaving the liquid equals the number returning to liquid from the vapor. We say that the system has reached equilibrium state at this stage. However, this is not static equilibrium and there is a lot of activity at the boundary between the liquid and the vapor. Thus, at equilibrium, the rate of evaporation is equal to the rate of condensation. It may be represented by H2O in liquid phase, which is a reversible reaction to H2O to vapor phase. The double half arrows indicate that the processes in both the directions are going on simultaneously. The mixture of reactants and products in the equilibrium state is called an equilibrium mixture. Equilibrium can be established for both physical processes and chemical reactions. The reactions may be fast or slow depending on the experimental conditions and the nature of the reactants. When the reactants in a closed vessel at a particular temperature react to give products, the concentrations of the reactants keep on decreasing, while those of products keep on increasing for some time, after which there is no change in the concentrations of either of the reactants or products. This stage of the system is the dynamic equilibrium, and the rates of the forward and reverse reactions become equal. It is due to this dynamic equilibrium stage that there is no change in the concentrations of various species in the reaction mixture. Based on the extent to which the reactions proceed to reach the static of chemical equilibrium, these may be classified in three groups. First one, the reactions that proceed nearly to completion and only negligible concentrations of the reactants are left. In some cases, it may not be even possible to detect these experimentally. Second one, the reactions in which only small amounts of products are formed and most of the reactants remain unchanged at equilibrium stage. Third one, the reactions in which the concentrations of the reactants and products are comparable when the system is in equilibrium. The extent of a reaction in equilibrium varies with the experimental conditions such as concentrations of reactants, temperature, etc. Optimization of the operational conditions is very important in industry and laboratory so that equilibrium is favorable in the direction of the desired product. Some important aspects of equilibrium involving physical and chemical processes are dealt in this unit along with the equilibrium involving ions in aqueous solutions, which is called as ionic equilibrium. Next, equilibrium in physical processes. The characteristics of system at equilibrium are better understood if we examine some physical processes. The most familiar examples are phase transformation processes. Example, solid to liquid, liquid to gas, solid to gas. These all are reversible reactions. Next, solid to liquid equilibrium. Ice and water kept in a perfectly insulated thermos flask, no exchange of heat between its contents and the surroundings at 273 Kelvin, and the atmospheric pressure are in equilibrium state, and the system shows interesting characteristic features. We observe that the mass of ice and water do not change with time and the temperature remains constant. However, the equilibrium is not static. The intense activity can be noticed at the boundary between ice and water. Molecules from the liquid water collide against ice and adhere to it, and some molecules of ice escape into liquid phase. There is no change of mass of ice and water, as the rates of transfer of molecules from ice into water and of reverse transfer from water into ice are equal at atmospheric pressure and 273 Kelvin. It is obvious that ice and water are in equilibrium only at particular temperature and pressure. For any pure substance at atmospheric pressure, the temperature at which the solid and liquid phases are at equilibrium is called the normal melting point or normal freezing point of the substance. The system here is in dynamic equilibrium, and we can infer the following. First point, both the opposing processes occur simultaneously. Second point, both the processes occur at the same rate so that the amount of ice and water remains constant. Next, liquid vapor equilibrium. This equilibrium can be better understood if we consider the example of a transparent box carrying a U-tube with mercury manometer. Drying agent like anhydrous calcium chloride or phosphorus pentaoxide is placed for a few hours in the box. After removing the drying agent by tilting the box on one side, a watch glass or petri dish containing water is quickly placed inside the box. It will be observed that mercury level in the right limb of the manometer slowly increases and finally attains a constant value. That is, the pressure inside the box increases and reaches a constant value. Also, the volume of water in the watch glass decreases. Initially, there was no water vapor inside the box. As water evaporated, the pressure in the box increased due to addition of water molecules into the gaseous phase inside the box. The rate of evaporation is constant. However, the rate of increase in pressure decreases with time due to condensation of vapor into water. Finally, it leads to an equilibrium condition when there is no net evaporation. This implies that the number of water molecules from the gaseous state into the liquid state also increases till the equilibrium is attained. That is, rate of evaporation equals to rate of condensation. At equilibrium, the pressure exerted by the water molecules at a given temperature remains constant and is called the equilibrium vapor pressure of water. Vapor pressure of water increases with temperature. If the above experiment is repeated with methyl alcohol, acetone and ether, it is observed that different liquids have different equilibrium vapor pressures at the same temperature, and the liquid which has a higher vapor pressure is more volatile and has a lower boiling point. If we expose 3 watch glasses containing separately 1 ml each of acetone, ethyl alcohol and water to atmosphere and repeat the experiment with different volumes of the liquids in a warmer room, it is observed that in all such cases the liquid eventually disappears and the time taken for complete evaporation depends on, first point, the nature of the liquid, second point, the amount of the liquid, and third point, the temperature. When the watch glass is open to the atmosphere, the rate of evaporation remains constant, but the molecules are dispersed into large volume of the room. As a consequence, the rate of condensation from vapor to liquid state is much less than the rate of evaporation. These are open systems and it is not possible to reach equilibrium in an open system. Water and water vapor are in equilibrium position at atmospheric pressure and at 100 degrees centigrade in a closed vessel. The boiling point of water is 100 degrees centigrade at 1.013 bar pressure. For any pure liquid at 1 atmospheric pressure, the temperature at which the liquid and vapors are at equilibrium is called normal boiling point of the liquid. Boiling point of the liquid depends on the atmospheric pressure. It depends on the altitude of the place. At high altitude, the boiling point decreases. Next, solid vapor equilibrium. Let us now consider the systems where solid sublime to vapor phase. If we place solid iodine in a closed vessel, after some time the vessel gets filled up with violet vapor and the intensity of color increases with time. After a certain time, the intensity of color becomes constant and at this stage equilibrium is attained. Hence, solid iodine sublimes to give iodine vapor and the iodine vapor condenses to give solid iodine. The equilibrium can be represented as I2 in solid phase gives rise to I2 vapor phase. This is reversible reaction. Other examples showing this kind of equilibrium are camphor solid state to camphor vapor state, NH4Cl solid state to NH4Cl vapor state. These two are the reversible reactions. Next, equilibrium involving dissolution of solid or gases in liquids. Solids in liquids. We know from our experience that we can dissolve only a limited amount of salt or sugar in a given amount of water at room temperature. If we make a thick sugar syrup solution by dissolving sugar at a higher temperature, sugar crystals separate out if we cool the syrup to the room temperature. We call it a saturated solution when no more of solute can be dissolved in it at a given temperature. The concentration of the solute in a saturated solution depends upon the temperature. In a saturated solution, a dynamic equilibrium exists between the solute molecules in the solid state and in the solution. Sugar solution to sugar solid state, and the rate of dissolution of sugar equals to rate of crystallization of sugar. Equality of the two rates of dynamic nature of equilibrium has been confirmed with the help of radioactive sugar. If we drop some radioactive sugar into saturated solution of non-radioactive sugar, then after some time radioactivity is observed both in the solution and in the solid sugar. Initially, there was no radioactive sugar molecules in the solution, but due to dynamic nature of equilibrium, there is exchange between the radioactive and non-radioactive sugar molecules between the two phases. The ratio of the radioactive to non-radioactive molecules in the solution increases till it attains a constant value. Next, gases in liquids. When a soda water bottle is opened, some of the carbon dioxide gas dissolved in it fizzes out rapidly. The phenomenon arises due to difference in solubility of carbon dioxide at different pressures. There is equilibrium between the molecules in the gaseous state and the molecules dissolved in the liquid under pressure. That is, CO2 in gaseous form gives rise to CO2 in solution. These two are reversible reaction. This equilibrium is governed by Henry's law, which states that the mass of a gas dissolved in a given mass of the solvent at any temperature is proportional to the pressure of the gas above the solvent. This amount decreases with increase of temperature. The soda water bottle is sealed under pressure of gas when its solubility in water is high. As soon as the bottle is opened, some of the dissolved carbon dioxide gas escaped to reach a new equilibrium condition required for the lower pressure, namely its partial pressure in the atmosphere. This is how the soda water in bottle, when left open to the air for some time, turns flat. It can be generalized that first one, for solids to liquid equilibrium, there is only one temperature melting point at 1 atm at which the two phases can coexist. If there is no exchange of heat with the surroundings, the mass of the two phases remain constant. Second point, for liquid to vapor equilibrium, the vapor pressure is constant at a given temperature. Third point, for dissolution of solids and liquids, the solubility is constant at a given temperature. Next, fourth point, for dissolution of gases in liquids, the concentration of a gas in liquid is proportional to the pressure of the gas over the liquid. These observations are summarized in table 6.1. So all these tables, everything I will be providing at the end of this audiobook. You can check it out. Okay, I will show this table. You can pause it and you can have a glance at it. Next, general characteristics of equilibria involving physical processes. For the physical processes discussed above, following characteristics are common to the system at equilibrium. First point, equilibrium is possible only in a closed system at a given temperature. Second one, both the opposing processes occur at the same rate and there is a dynamic but stable condition. Third point, all measurable properties of the system remain constant. Fourth point, when equilibrium is attained for a physical process, it is characterized by constant value of one of its parameters at a given temperature. Table 6.1 lists such quantities. Fifth point, the magnitude of such quantities at any stage indicates the extent to which the physical process has proceeded before reaching equilibrium. Next, equilibrium in chemical processes, dynamic equilibrium. Analogous to the physical system, Chemical reactions also attain a state of equilibrium. These reactions can occur both in forward and backward directions. When the rates of the forward and reverse reactions become equal, the concentrations of the reactants and the products remain constant. This is the stage of chemical equilibrium. This equilibrium is dynamic in nature as it consists of a forward reaction in which the reactants give products and reverse reaction in which products give the original reactants. For a better comprehension, let us consider a general case of a reversible reaction. A plus B gives rise to C plus D. This is reversible. With passage of time, there is accumulation of the products C and D and depletion of the reactants A and B. This leads to a decrease in the rate of the forward reaction and an increase in the rate of the reverse reaction. Eventually, the two reactions occur at the same rate and the system reaches a state of equilibrium. You can check the figure 6.2, attainment of chemical equilibrium. This is the figure. Eventually, the two reactions occur at the same rate and the system reaches a state of equilibrium. Similarly, the reaction can reach the state of equilibrium even if we start with only C and D, that is, no A and B being present initially, as the equilibrium can be reached from either direction. The dynamic nature of chemical equilibrium can be demonstrated in the synthesis of ammonia by Haber's process. In a series of experiments, Haber started with known amounts of dinitrogen and the dihydrogen maintained at high temperature and pressure and at regular intervals determined the amount of ammonia present. He was successful in determining also the concentration of unreacted dihydrogen and dinitrogen, shows that after a certain time the composition of the mixture remains the same even though some of the reactants are still present. This constancy in composition indicates that the reaction has reached equilibrium. In order to understand the dynamic nature of the reaction, synthesis of ammonia is carried out with exactly the same starting conditions, but using D2 deuterium in place of H2. The reaction mixture starting either with H2 or D2 reach equilibrium with the same composition, except that D2 and ND3 are present instead of H2 and NH3. After equilibrium is attained, these two mixtures are mixed together and left for a while. Later, when this mixture is analyzed, it is found that the concentration of ammonia is just the same as before. However, when this mixture is analyzed by a mass spectrometer, it is found that ammonia and all deuterium containing forms of ammonia and dihydrogen and its deuterated forms are present. Thus, one can conclude that scrambling of H and D atoms in the molecules must result from a continuation of the forward and reverse reactions in the mixture. If the reaction had simply stopped when they reached equilibrium, then there would have been no mixing of isotopes in this way. Use of isotope deuterium in the formation of ammonia clearly indicates that chemical reactions reach a state of dynamic equilibrium in which the rates of forward and reverse reactions are equal and there is no net change in composition. Equilibrium can be attained from both sides, whether we start reaction by taking H2 and N2 and get NH3 or by taking NH3 and decomposing it into N2 and H2. Next, similarly, let us consider the reaction H2 plus I2 gives rise to 2HI. If we start with equal initial concentration of H2 and I2, the reaction proceeds in the forward direction and the concentration of H2 and I2 decreases while that of HI increases until all this become constant at equilibrium. Figure 6.5. So let's see figure 6.5. So here is the figure. Chemical equilibrium in the reaction H2 plus I2 gives 2HI can be obtained from either direction. So this is the figure. We can also start with HI alone and make the reaction to proceed in the reverse direction. The concentration of HI will decrease and concentration of H2 and I2 will increase until they all become constant when equilibrium is reached. If total number of H and I atoms are same in the given volume, the same equilibrium mixture is obtained whether we start it from pure reactants or pure product. Next, law of chemical equilibrium and equilibrium constant. A mixture of reactants and products in the equilibrium state is called an equilibrium mixture. In this section, we shall address a number of important questions about the composition of equilibrium mixtures. What is the relationship between the concentrations of reactants and products in an equilibrium mixture? How can we determine equilibrium concentrations from initial concentrations? What factors can be exploited to alter the composition of an equilibrium mixture? The last question in particular is important when choosing conditions for synthesis of industrial chemicals such as H2, NH3, CaO, etc. To answer these questions, let us consider a general reversible reaction. A plus B gives rise to C plus D, which is a reversible reaction, where A plus B are the reactants and C and D are the products in the balanced chemical equation. On the basis of the experimental studies of many reversible reactions, the Norwegian chemist Cato Maximilian Gullberg and Peter Wage proposed in 1864 that the concentrations in an equilibrium mixture are related by the following equilibrium equation. So here this is the equilibrium equation, you can check it out, where Kc is the equilibrium constant and the expression on the right side is called the equilibrium constant expression. The equilibrium equation is also known as law of mass action because in the early days of chemistry, concentration was called active mass. In order to appreciate their work better, let us consider a reaction between gaseous H2 and I2 carried out in the sealed vessel at 731 K. 6 sets of experiments with varying initial conditions were performed, starting with only gaseous H2 and I2 in a sealed reaction vessel in first 4 experiments and only Hi in other 2 experiments. Experiments 1, 2, 3 and 4 were performed taking different concentrations of H2 and or I2, and with time it was observed that intensity of the purple color remained constant and the equilibrium was attained. Similarly, for experiments 5 and 6, the equilibrium was attained from the opposite direction. Data obtained from all 6 sets of experiments are given in table 6.2. It is evident from the experiments 1, 2, 3 and 4 that number of moles of dihydrogen reacted equals to number of moles of iodine reacted equals to 1 by 2 number of moles of Hi formed. Also, experiments 5 and 6 indicate that this is the one. Knowing the above facts, in order to establish a relationship between concentrations of the reactants and products, several combinations can be tried. Let us consider the simple reaction. So this is a reaction, you can check it. It can be seen from table 6.3 that if we put the equilibrium concentrations of the reactants and products, the above expression is far from constant. However, if we consider the expression given below, we find that this expression gives constant value as shown in table 6.3 in all the 6 cases. So this is table 6.3, expression involving the equilibrium concentration of reactants. You can pause it and please check it. It can be seen that in this expression, the power of the concentration for reactants and products are actually the stoichiometric coefficients in the equation for the chemical reaction. Thus, for the reaction H2 gaseous form plus I2 gaseous form gives rise to 2HI gaseous form. Following equation 6.1, the equilibrium constant Kc is written as given below. Generally, the subscript EQ used for equilibrium is omitted from the concentration terms. It is taken for granted that the concentrations in the expression for Kc are equilibrium values. We therefore write the given equation. The subscript C indicates that Kc is expressed in concentrations of moles per liter. At a given temperature, the product of the concentrations of the reaction products raised to the respective stoichiometric coefficient in the balanced chemical equation divided by the product of the concentrations of the reactants raised to their individual stoichiometric coefficients has a constant value. This is known as equilibrium law or law of chemical equilibrium. The equilibrium constant for a general reaction A small a capital A plus small b capital B gives rise to small c capital C plus small d capital D is expressed as given below, where A, B, C and D are the equilibrium concentrations of the reactants and products. Equilibrium constant for the reaction, the given reaction is written as in the given form. Please check it out. Molar concentration of different species is indicated by enclosing these in square brackets, and as mentioned above, it is simplified that these are equilibrium concentrations. While writing expression for equilibrium constant, symbol for phases S, L, G are generally ignored. Let us write equilibrium constant for the reaction H2 plus I2 gives rise to 2HI as Kc HI whole square by H2 I2 equals to X. The equilibrium constant for the reverse reaction at the same temperature is given below. Thus Kc equals to 1 by Kc. Equilibrium constant for the reverse reaction is the inverse of the equilibrium constant for the reaction in the forward direction. If we change the stoichiometric coefficients in a chemical equation by multiplying throughout by a factor, then we must make sure that the expression for equilibrium constant also reflects that change. For example, if the reaction 6.5 is written as, this is the given below, the equilibrium constant for the above reaction is given by this equation. On multiplying the equation 6.5 by n, we get, this is the equation, figure 6.11, reaction 6.11. Therefore, equilibrium constant for the reaction is equal to Kcn. These findings are summarized in table 6.4. It should be noted that because the equilibrium constant Kc and Kc have different numerical values, it is important to specify the form of the balanced chemical equation when quoting the value of equilibrium constant. So here is table 6.4 mentioning relations between equilibrium constant for a general reactions and its multiples. You can check it out. Next, homogeneous equilibria. In a homogeneous system, all the reactants and products are in the same phase. For example, in the gaseous reaction, N2 plus 3H2 gives rise to 2NH3. Reactants and products are in the homogeneous phase. Similarly, for the reactions given below, all the reactants and products are in homogeneous solution phase. We shall now consider equilibrium constant for some homogeneous reactions. Next, equilibrium constant in gaseous systems. So far, we have expressed equilibrium constant of the reactions in terms of molar concentrations of the reactants and products and used the symbol Kc for it. For reactions involving gases, however, it is usually more convenient to express the equilibrium constant in terms of partial pressure. The ideal gas equation is written as PV equals to nRT. P equals to N by V RT. Here P is the pressure in PA, N is the number of moles of the gas, V is the volume in M to the power of 3 and T is the temperature in Kelvin. Therefore, N by V is concentration expressed in moles per M3. If concentration C is in mole per liter or mole per dm3 and P is in bar, then P equals to CRT. We can also write P equals to RT, gaseous. Here R equals to 0.0831 bar liter per mole K. At constant temperature, the pressure of the gas is proportional to its concentration, that is P proportional to gas. For reaction in equilibrium, this is the given one. Okay, these are the equations. Please check it out. 6.13. In this example, Kp equals to Kc, that is both equilibrium constants are equal. However, this is not always the case. For example, in the given reaction, this is the one. Please check it. Pause it and check it. Okay. To equation 6.14. Similarly, for a general reaction, AA plus BB gives rise to CC plus DD, which is an equilibrium reaction. This is the total reaction 6.15, where delta N equals to number of moles of gaseous products minus number of moles of gaseous reactants in the balanced chemical equation. It is necessary that while calculating the value of Kp, pressure should be expressed in bar because standard state for pressure is 1 bar. We know from unit 1 that 1 Pascal Pa equals to 1 Nm minus 2 and 1 bar equals to 10 to the power of 5 pascals. Kp values for a few selected reactions at different temperatures are given in table 6.5. So let's see table 6.5 mentioning equilibrium constants Kp for a few selected reactions. Please check it out. Next, heterogeneous equilibria. Equilibrium in a system having more than one phase is called heterogeneous equilibrium. The equilibrium between water vapor and liquid water in a closed container is an example of the heterogeneous equilibrium. H2O liquid form gives rise to H2O gaseous form. In this example, there is a gas phase and a liquid phase. In the same way, equilibrium between a solid and its saturated solution is a heterogeneous equilibrium. Heterogeneous equilibria often involve pure solids or liquids. We can simplify equilibrium expressions for the heterogeneous equilibria involving a pure liquid or a pure solid as the molar concentration of a pure solid or liquid is constant. In other words, if the substance X is involved, then Xs and Xl are constant. Whatever the amount of X is taken, contrary to this, X gaseous form and X aqueous form will vary as the amount of X in a given volume varies. Let us take thermal dissociation of calcium carbonate, which is an interesting and important example of heterogeneous chemical equilibrium. So this is the one, please check it out. Since CaCO3 solid state and CaCaO solid state are both constant, therefore modified equilibrium constant for the thermal decomposition of calcium carbonate will be Kc equals to CO2 gaseous form, or Kp equals to PCO2. Next, here a green box is given. Let us see what is it. Units of equilibrium constant. The value of equilibrium constant Kc can be calculated by substituting the concentration terms in mole per liter, and for Kp partial pressure is substituted in Pa, Kpa, bar or atm. This results in units of equilibrium constant based on molarity or pressure, unless the exponents of both the numerator and denominator are same. For the reactions, H2 gaseous form plus I2 gaseous form gives rise to 2Hi. Kc and Kp have no unit. N2O4 gaseous form gives rise to 2NO2 gaseous form. Kc has unit mole per liter and Kp has unit bar. Equilibrium constants can also be expressed as dimensionless quantities if the standard state of reactants and products are specified. For a pure gas, the standard state is 1 bar. Therefore, a pressure of 4 bar in standard state can be expressed as 4 bar by 1 bar equals to 4, which is a dimensionless number. Standard state C0 for a solute is 1 molar solution and all concentrations can be measured with respect to it. The numerical value of equilibrium constant depends on the standard state chosen. Thus, in this system, both Kp and Kc are dimensionless quantities but have different numerical values due to different standard states. This shows that at a particular temperature, there is a constant concentration or pressure of CO2 in equilibrium with CaO and CaCO3. Experimentally, it has been found that at 1100 K, the pressure of CO2 in equilibrium with CaCO3 and CaO is 2.0 into 10 to the power of 5 pascals. Therefore, equilibrium constant at 1100 K for the above reaction is given below. Similarly, in the equilibrium between nickel carbon monoxide and nickel carbonyl used in the purification of nickel is Li solid state plus 4CO gaseous state gives rise to NiCO4 gaseous state. The equilibrium constant is written as in this way. It must be remembered that for the existence of heterogeneous equilibrium, pure solids or liquids must also be present at equilibrium, but their concentrations or partial pressures do not appear in the expression of the equilibrium constant. In the reaction, Ag2O solid form plus 2HNO3 aqueous form gives rise to 2AgNO3 aqueous form plus H2O liquid form. Next, applications of equilibrium constants. Before considering the applications of equilibrium constants, let us summarize the important features of equilibrium constants as follows. First one, expression for equilibrium constant is applicable only when concentrations of the reactants and products have obtained constant value at equilibrium state. Second point, the value of equilibrium constant is independent of initial concentrations of the reactants and products. Third point, equilibrium constant is temperature dependent, having one unique value for a particular reaction represented by balanced equation to given temperature. Fourth point, the equilibrium constant for the reverse reaction is equal to the inverse of the equilibrium constant for the forward reaction. Fifth point. The equilibrium constant K for a reaction is related to the equilibrium constant of the corresponding reaction, whose equation is obtained by multiplying or dividing the equation for the original reaction by a small integer. Let us consider applications of equilibrium constant too. First one, predict the extent of a reaction on the basis of its magnitude. Second one, predict the direction of the reaction. And third one, calculate equilibrium concentrations. Next, predicting the extent of the reaction. The numerical value of the equilibrium constant for a reaction indicates the extent of the reaction. But it is important to note that an equilibrium constant does not give any information about the rate at which the equilibrium is reached. The magnitude of Kc and Kp is directly proportional to the concentrations of products, as these appear in the numerator and equilibrium constant expression, and inversely proportional to the concentrations of the reactants. This implies that a high value of K is suggestive of a high concentration of products and vice versa. We can make the following generalizations concerning the composition of equilibrium mixtures. So, if Kc greater than 10 to the power of 3 products predominate over reactants, that is, if Kc is very large, the reaction proceeds nearly to completion. Consider the following examples. So, these are the examples A, B and C. Please check it out. If Kc less than 10 to the power of minus 3 reactants predominate over products, that is, if Kc is very small, the reaction proceeds rarely. Consider the following examples. A. The decomposition of H2O into H2 and O2 at 500 K has a very small equilibrium constant, Kc equals to 4.1 into 10 to the power of minus 48. Next, B. N2 gaseous form plus O2 gaseous form gives rise to 2NO gaseous form. At 298 Kelvin has Kc equals to 4.8 into 10 to the power of minus 31. If Kc is in the range of 10 to the power of minus 3 to 10 to the power of 3, appreciable concentrations of both reactants and products are present. Consider the following examples. For reaction of H2 with I2 to give Hi, Kc equals to 57 at 700 K. Also, gas phase decomposition of N2O4 to NO2 is another reaction with a value of Kc equals to 4.64 into 10 to the power of minus 3 at 25 degrees centigrade, which has neither too small nor too large. Hence, equilibrium mixtures contain appreciable concentrations of both N2O4 and NO2. These generalizations are illustrated in figure 6.6. So this is the figure, please pause it and check it out. Next, predicting the direction of a reaction. The equilibrium constant helps in predicting the direction in which a given reaction will proceed at any stage. For this purpose, we calculate the reaction coefficient Q. The reaction coefficient Q, Qc with molar concentrations and Qp with partial pressures is defined in the same way as the equilibrium constant Kc, except that the concentrations in Qc are not necessarily equilibrium values. For a general reaction, A plus B gives rise to C plus D. Then, if Qc greater than Kc, the reaction will proceed in the direction of reactants, reverse reaction. If Qc less than Kc, the reaction will proceed in the direction of the products, forward reaction. If Qc equals to Kc, the reaction mixture is already at equilibrium. Consider the gaseous reaction of H2 with I2. H2 in gaseous form plus I2 gaseous form gives rise to 2Hi, Kc equals to 57 at 700 K. Suppose we have molar concentrations H2 0.10 molar, I2 0.20 and Hi 0.40. The subscript T on the concentration symbols means that the concentrations were measured at some arbitrary time T, not necessarily at equilibrium. Thus, the reaction coefficient Qc at this stage of the reaction is given by, this is the one, Qc equals to 8.0. Now, in this case, Qc does not equal Kc. So, the mixture H2, I2 and Hi is not at equilibrium. That is, more H2 and I2 will react to form more Hi and their concentrations will decrease till Qc equals to Kc. The reaction coefficient Qc is equal in predicting the direction of reaction by comparing the values of Qc and Kc. Thus, we can make the following generalizations concerning the direction of the reaction. Figure 6.7. So, this is the figure. Please check it out. Next, calculating equilibrium concentrations. In case of a problem in which we know the initial concentrations but do not know any of the equilibrium concentrations, the following three steps shall be followed. Step 1. Write the balanced equation for the reaction. Step 2. Under the balanced equation, make a table that lists for each substance involved in the reaction. A. The initial concentration. B. The change in concentration on going to equilibrium. And C. The equilibrium concentration. In constructing the table, define X as the concentration of one of the substances that reacts on going to equilibrium. Then use the stoichiometry of the reaction to determine the concentrations of the other substances in terms of X. Step 3. Substitute the equilibrium concentrations into the equilibrium equation for the reaction and solve for X. If you are to solve a quadratic equation, choose the mathematical solution that makes chemical sense. Step 4. Calculate the equilibrium concentrations from the calculated value of X. Step 5. Check your results by substituting them into the equilibrium equation. Next, relationship between equilibrium constant K, reaction coefficient Q and Gibbs energy G. The value of Kc for a reaction does not depend on the rate of the reaction. However, as you have studied in Unit 5, it is directly related to the thermodynamics of the reaction and in particular to the change in Gibbs energy, delta G. If delta G is negative, then the reaction is spontaneous and proceeds in the forward direction. Delta G is positive, then reaction is considered non-spontaneous. Instead, as reverse reaction would have a negative delta G, the products of the forward reaction shall be converted to the reactants. Delta G is 0. Reaction has achieved equilibrium. At this point, there is no longer any free energy left to drive the reaction. A mathematical expression of this thermodynamic view of equilibrium can be described by the following equation. Delta G equals to delta G plus RT in Q, where G is standard Gibbs energy. At equilibrium, when delta G equals to 0 and Q is equal to Kc, the equation 6.21 becomes, this is the one, 6.22. Please check it. Taking anti-log of both sides, we get reaction 6.23. Hence, using the equation 6.23, the reaction spontaneity can be interpreted in terms of the value of delta G. If delta G is less than 0, then minus delta G by RT is positive and E minus delta dG by RT greater than 1, making K greater than 1, which implies a spontaneous reaction or the reaction which proceeds in the forward direction to such an extent that the products are present predominantly. If delta G greater than 0, then minus delta G by RT is negative and E minus delta G less than by RT 1, that is K less than 1, which implies a non-spontaneous reaction or a reaction which proceeds in the forward direction to such a small degree that only a very minute quantity of product is formed. Next, factors affecting equilibrium. One of the principal goals of chemical synthesis is to maximize the conversion of the reactants to products while minimizing the expenditure of energy. This implies maximum yield of products at mild temperature and pressure conditions. If it does not happen, then the experimental conditions need to be adjusted. For example, in the Haber process for the synthesis of ammonia from N2 and H2, the choice of experimental conditions is of real economic importance. Annual world production of ammonia is about 100 million tons, primarily for use as fertilizers. Equilibrium constant Kc is independent of initial concentrations, but if a system at equilibrium is subjected to a change in the concentration of one or more of the reacting substances, then the system is no longer at equilibrium and net reaction takes place in some direction until the system returns to the equilibrium once again. Similarly, a change in temperature or pressure of the system may also alter the equilibrium. In order to decide what course the reaction adopts and make a qualitative prediction about the effect of a change in conditions on equilibrium, we use Le Chatelier's principle. It states that a change in any of the factors that determine the equilibrium conditions of a system will cause the system to change in such a manner so as to reduce or to counteract the effect of the change. This is applicable to all physical and chemical equilibria. We shall now be discussing factors which can influence the equilibrium. Effect of concentration change. In general, when equilibrium is disturbed by the addition or removal of any reactant or products, Le Chatelier's principle predicts that, first one, the concentration stress of an added reactant or product is relieved by net reaction in the direction that consumes the added substance. Second point, the concentration stress of a removed reactant or product is relieved by net reaction in the direction that replenishes the removed substance. Or, in other words, when the concentration of any of the reactants or products in a reaction at equilibrium is changed, the composition of the equilibrium mixture changes so as to minimize the effect of concentration changes. Let us take the reaction H2 plus I2, which are gaseous forms, gives rise to 2HI. If H2 is added to the reaction mixture at equilibrium, then the equilibrium of the reaction is disturbed. In order to restore it, the reaction proceeds in a direction wherein H2 is consumed. That is, more H2 and I2 react to form HI, and finally the equilibrium shifts in right forward direction. This is in accordance with the Le Chatelier's principle, which implies that in case of addition of a reactant or product, a new equilibrium will be set up in which the concentration of the reactant and product should be less than what it was after the addition, but more than what it was in the original mixture. So here is figure 6.8. Please check it out. The same point can be explained in terms of the reaction coefficient QC. Addition of hydrogen at equilibrium results in value of QC being less than Kc. Thus, in order to attain equilibrium, again reaction moves in the forward direction. Similarly, we can say that removal of the product also boosts the forward reaction and increases the concentration of the products, and this has great commercial application in cases of reactions where the product is a gas or a volatile substance. In case of manufacture of ammonia, ammonia is liquefied and removed from the reaction mixture so that reaction keeps moving in forward direction. Similarly, in the large scale production of CaO from CaCO3, constant removal of CO2 from the kiln drives the reaction to completion. It should be remembered that continuous removal of a product maintains QC at a value less than Kc and reaction continues to move in the forward direction. Effect of concentration and experiment. This can be demonstrated by the following reaction. This is a reaction, please check it. A reddish color appears on adding 2 drops of 0.002 molar potassium thiocyanate solution to 1 ml of 0.2 molar iron 3 nitrate solution due to the formation of FeSCN plus 2. The intensity of the red color becomes constant on attaining equilibrium. This equilibrium can be shifted in either forward or reverse directions depending on our choice of adding a reactant or a product. The equilibrium can be shifted in the opposite direction by adding reagents that remove Fe plus 3 or SCN minus ions. For example, oxalic acid H2C2O4 reacts with Fe plus 3 ions to form the stable complex ion FeC2O43 minus 3, thus decreasing the concentration of free Fe plus 3 ions. In accordance with the Le Chatelier's principle, the concentration stress of removed Fe plus 3 is relieved by dissociation of FeSCN plus 2 to replenish the Fe plus 3 ions. Because the concentration of FeSCN plus 2 decreases, the intensity of red color decreases. Addition of aqueous HeCl2 also decreases red color because Hg plus 2 reacts with SCN minus ions to form stable complex ion. Removal of free SCN minus shifts the equilibrium in equation 6.24 from right to left to replenish SCN minus ions. Addition of potassium thiocyanate, on the other hand, increases the color intensity of the solution as it shifts the equilibrium to right. Next, effect of pressure change. A pressure change obtained by change in the volume can affect the yield of products in case of gaseous reaction, where the total number of moles of gaseous reactants and the total number of moles of gaseous products are different. In applying Le Chatelier's principle to a heterogeneous equilibrium, the effect of pressure changes on solids and liquids can be ignored because the volume of a solution or liquid is nearly independent of pressure. Consider the equation. CO plus 3H2 gives rise to CH4 plus H2O. Here, 4 moles of gaseous reactants become 2 moles of gaseous products. Suppose equilibrium mixture kept in a cylinder fitted with a piston at constant temperature is compressed to 1/2 of its original volume. Then total pressure will be doubled. The partial pressure and therefore concentration of reactants and products have changed, and the mixture is no longer at equilibrium. The direction in which the reaction goes to re-establish equilibrium can be predicted by applying the Le-Chatelier's principle. Since pressure has doubled, the equilibrium now shifts in the forward direction, a direction in which the number of moles of the gas or pressure decreases. This can also be understood by using reaction coefficient QC. Let COH2CH4 and H2O be the molar concentrations at an equilibrium for methanation reaction. When volume of the reaction mixture is halved, the partial pressure and the concentration are doubled. We obtain the reaction coefficient by replacing each equilibrium concentration by double its value. As QC less than Kc, the reaction proceeds in the forward direction. In reaction, C plus CO2 gives rise to 2CO. When pressure is increased, the reaction goes in the reverse direction because the number of moles of gas increases in the forward direction. Next one, effect of inert gas addition. If the volume is kept constant and an inert gas such as argon is added which does not take part in the reaction, the equilibrium remains undisturbed. It is because the addition of an inert gas at constant volume does not change the partial pressures or the molar concentrations of the substance involved in the reaction. The reaction coefficient changes only if the added gas is a reactant or product involved in the reaction. Next, effect of temperature change. Whenever an equilibrium is disturbed by a change in the concentration, pressure or volume, the composition of the equilibrium mixture changes because the reaction coefficient QC no longer equals the equilibrium constant Kc. However, when a change in temperature occurs, the value of equilibrium constant Kc is changed. In general, the temperature dependence of the equilibrium constant depends on the sign of delta H for the reaction. First one, the equilibrium constant for an exothermic reaction decreases as the temperature increases. Next, the equilibrium constant for an endothermic reaction increases as the temperature increases. Temperature changes affect the equilibrium constant and rates of reactions. Production of ammonia according to the reaction. Delta H equals to 92.38 kilojoules per mole is an exothermic process. According to Le-Chatelier's principle, raising the temperature shifts the equilibrium to left and decreases the equilibrium concentration of ammonia. In other words, low temperature is favorable for high yield of ammonia, but practically very low temperatures slow down the reaction and thus a catalyst is used. Effect of temperature. An experiment. Effect of temperature on equilibrium can be demonstrated by taking NO2 gas, brown in color, which dimerizes into N2O4 gas, colorless. NO2 gas prepared by addition of Cu turnings to concentration HNO3 is collected in 2 5 ml test tubes and stopper sealed with araldite. 3 250 ml beakers 1, 2 and 3 containing freezing mixtures, water at room temperature and hot water 363 Kelvin respectively are taken. Figure 6.9. Both the test tubes are placed in a beaker 2 for 8 to 10 minutes. After this, one is placed in beaker 1 and the other in beaker 3. The effect of temperature on direction of reaction is depicted very well in this experiment. At low temperatures in beaker 1, the forward reaction of formation of N2O4 is preferred, as reaction is exothermic and thus intensity of brown color due to NO2 decreases. While in beaker 3, high temperature favors the reverse reaction of formation of NO2 and thus the brown color intensifies. Effect of temperature can also be seen in this endothermic reaction. At room temperature, the equilibrium mixture is blue due to COCl4-2. When cooled in a freezing mixture, the color of the mixture turns pink due to COH2O6+3. So here is the figure of this experiment. Please check it out. Figure 6.9, effect of temperature on equilibrium for the given reaction. Next, effect of a catalyst. A catalyst increases the rate of the chemical reaction by making available a new low energy pathway for the conversion of reactants to products. It increases the rate of forward and reverse reactions that pass through the same transition state and does not affect the equilibrium. Catalyst lowers the activation energy for the forward and reverse reactions by exactly the same amount. Catalyst does not affect the equilibrium composition of a reaction mixture. It does not appear in the balanced chemical equation or in the equilibrium constant expression. Let us consider the formation of NH3 from dinitrogen and dihydrogen, which is a highly exothermic reaction and proceeds with decrease in total number of moles formed as compared to the reactants. Equilibrium constant decreases with increase in temperature. At low temperature, rate decreases and it takes a long time to reach at equilibrium, whereas high temperatures give satisfactory rates but poor yields. German chemist Fritz Haber discovered that a catalyst consisting of iron catalyzes the reaction to occur at a satisfactory rate at temperatures where the equilibrium concentration of NH3 is reasonably favorable. Since the number of moles formed in the reaction is less than those of reactants, the yield of NH3 can be improved by increasing the pressure. Optimum conditions of temperature and pressure for the synthesis of NH3 using catalyst are around 500 degrees Celsius and 200 atm. Similarly, in manufacture of sulfuric acid by contact process, though the value of K is suggestive of reaction going to completion, but practically the oxidation of SO2 to SO3 is very slow. Thus, platinum or divanadium pentaoxide V2O5 is used as catalyst to increase the rate of the reaction. Note, if a reaction has an exceedingly small K, a catalyst would be of little help. Next, ionic equilibrium in solution. Under the effect of change of concentration on the direction of equilibrium, you have incidentally come across with the following equilibrium which involves ions. There are numerous equilibria that involve ions only. In the following sections, we will study the equilibria involving ions. It is well known that the aqueous solution of sugar does not conduct electricity. However, when common salt is added to water, it conducts electricity. Also, the conductance of electricity increases with an increase in concentration of common salt. Michael Faraday classified the substances into two categories based on their ability to conduct electricity. One category of substances conduct electricity in their aqueous solution and are called electrolytes, while the other do not and are thus referred to as non-electrolytes. Faraday further classified electrolytes into strong and weak electrolytes. Strong electrolytes on dissolution in water are ionized almost completely, while the weak electrolytes are only partially dissociated. For example, an aqueous solution of sodium chloride is comprised entirely of sodium ions and chloride ions, while that of acetic acid mainly contains unionized acetic acid molecules and only some acetate ions and hydronium ions. This is because there is almost 100% ionization in case of sodium chloride as compared to less than 5% ionization of acetic acid, which is a weak electrolyte. It should be noted that in weak electrolytes, equilibrium is established between ions and the unionized molecules. This type of equilibrium involving ions in aqueous solution is called ionic equilibrium. Acids, bases and salts come under the category of electrolytes and may act as either strong or weak electrolytes. Next, acids, bases and salts. Acids, bases and salts find widespread occurrence in nature. Hydrochloric acid present in the gastric juice is secreted by the lining of our stomach in a significant amount of 1.2 to 1.5 liters per day and is essential for digestive processes. Acetic acid is known to be the main constituent of vinegar. Lemon and orange juices contain citric and ascorbic acids, and tartaric acid is found in tamarind paste. As most of the acids taste sour, the word acid has been derived from a Latin word acidus meaning sour. Acids are known to turn blue litmus paper into red and liberate dihydrogen on reacting with some metals. Similarly, bases are known to turn red litmus paper blue, taste bitter and feel soapy. A common example of a base is washing soda used for washing purposes. When acids and bases are mixed in the right proportion, they react with each other to give salts. Some commonly known examples of salts are sodium chloride, barium sulfate, sodium nitrate. Sodium chloride is an important component of our diet and is formed by reaction between hydrochloric acid and sodium hydroxide. It exists in solid state as a cluster of positively charged sodium ions and negatively charged chloride ions, which are held together due to electrostatic interactions between oppositely charged species. The electrostatic forces between two charges are inversely proportional to dielectric constant of the medium. Water, a universal solvent, possesses a very high dielectric constant of 80. Thus, when sodium chloride is dissolved in water, the electrostatic interactions are induced by a factor of 80 and this facilitates the ions to move freely in the solution. Also, they are well separated due to hydration with water molecules. Next, comparing the ionization of hydrochloric acid with that of acetic acid in water, we find that though both of them are polar covalent molecules, former is completely ionized into its constituent ions while the latter is only partially ionized. The extent to which ionization occurs depends upon the strength of the bond and the extent of solvation of ions produced. The terms dissociation and ionization have earlier been used with different meaning. Dissociation refers to the process of separation of ions in water already existing as such in the solid state of the solute, as in sodium chloride. On the other hand, ionization corresponds to a process in which a neutral molecule splits into charges ions in the solution. Here we shall not distinguish between the two and the use of two terms interchangeably. Next, Arrhenius concept of acids and bases. According to Arrhenius theory, acids are substances that dissociates in water to give hydrogen ions and bases are substances that produce hydroxyl ions. The ionization of an acid HX can be represented by the following equations. A bare proton H plus is very reactive and cannot exist freely in aqueous solutions. Thus, it bonds to the oxygen atom of a solvent water molecule to give trigonal pyramidal hydronium ion H3O plus. In this chapter, we shall use H plus and H3O plus interchangeably to mean the same, that is a hydrated proton. Similarly, a base molecule like MOH ionizes in aqueous solution according to the equation. The hydroxyl ion also exists in the hydrated form in the aqueous solution. Arrhenius concept of acid and base, however, suffers from the limitation of being applicable only to aqueous solutions and also does not account for the basicity of substances like ammonia which do not possess a hydroxyl group. The Danish chemist Johannes Bronsted and the English chemist Thomas M. Lowry gave a more general definition of acids and bases. According to Bronsted-Lowry theory, acid is a substance that is capable of donating a hydrogen ion H+, and bases are substances capable of accepting a hydrogen ion H+. In short, acids are proton donors and bases are proton acceptors. Consider the example of dissolution of NH3 in H2O represented by the following equation. Please check the equation here. The basic solution is formed due to the presence of hydroxyl ions. In this reaction, water molecules act as proton donor and ammonia molecule acts as proton acceptor and are thus called Lowry-Bronsted acid and base respectively. In the reverse reaction, H plus is transferred from NH4 plus to OH minus. In this case, NH4 plus acts as Bronsted acid while OH minus acts as Bronsted base. The acid-base pairs that differs only by one proton is called a conjugate acid-base pair. Therefore, OH minus is called the conjugate base of an acid H2O and NH4 plus is called conjugate acid of the base NH3. If Bronsted acid is a strong acid, then its conjugate base is a weak base and vice versa. It may be noted that conjugate acid has one extra proton and each conjugate base has one less proton. Consider the example of ionization of hydrochloric acid in water. HCl acts as an acid by donating a proton to H2O molecule, which acts as a base. It can be seen in the above equation that water acts as a base because it accepts a proton. The species H3O plus is produced when water accepts a proton from HCl. Therefore, Cl minus is a conjugate base of HCl and HCl is a conjugate acid of base Cl minus. Similarly, H2O is a conjugate base of an acid H3O plus and H3O plus is a conjugate acid of base H2O. It is interesting to observe the dual role of water as an acid and a base. In case of reaction with HCl, water acts as a base, while in case of ammonia, it acts as an acid by donating a proton. Next, Lewis acids and bases. G.N. Lewis in 1923 defined an acid as a species which accepts electron pair and a base which donates an electron pair. As far as bases are concerned, there is no much difference between Bronsted-Lowry and Lewis concepts as the base provides a lone pair in both the cases. However, in Lewis concept, many acids do not have proton. A typical example is a reaction of electron deficient species BF3 with NH3. BF3 does not have a proton but still acts as an acid and reacts with NH3 by accepting its lone pair of electrons. The reaction can be represented by in this way. Electron deficient species like AlCl3, CO plus 3, Mg plus 2, etc. can act as Lewis acids, while species like H2O, NH3OH minus, etc., which can donate a pair of electrons, can act as Lewis bases. Next, ionization of acids and bases. Arrhenius concept of acids and bases becomes useful in case of ionization of acids and bases, as mostly ionizations in chemical and biological systems occur in aqueous medium. Strong acids like perchloric acid, HClO4, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid and sulfuric acid are termed strong because they are almost completely dissociated into their constituent ions in an aqueous medium, thereby acting as proton donors. Similarly, strong bases like lithium hydroxide, sodium hydroxide, potassium hydroxide, cesium hydroxide and barium hydroxide are almost completely dissociated into ions in an aqueous medium, giving hydroxyl ions OH-. According to Arrhenius concept, they are strong acids and bases as they are able to completely dissociate and produce H3O plus and OH minus ions respectively in the medium. Alternatively, the strength of an acid or base may also be gauged in terms of Bronsted-Lowry concept of acids and bases, wherein a strong acid means a good proton donor and a strong base implies a good proton acceptor. Consider the acid-base dissociation equilibrium of a weak acid Ha. In section 6.10.2, we saw that acid dissociation equilibrium is dynamic, involving a transfer of proton in forward and reverse directions. Now the question arises that if the equilibrium is dynamic, then with passage of time, which direction is favored? What is the driving force behind it? In order to answer these questions, we shall deal into the issue of comparing the strengths of two acids or bases involved in the dissociation equilibrium. Consider the two acids HA and H3O plus present in the above mentioned acid dissociation equilibrium. We have to see which amongst them is a stronger proton donor. Whichever exceeds in its tendency of donating a proton over the other shall be termed as a stronger acid, and equilibrium will shift in the direction of weaker acid. Say if HA is a stronger acid than H3O plus, then HA will donate protons and not H3O plus, and the solution will mainly contain A minus and H3O plus ions. The equilibrium moves in the direction of formation of weaker acid and weaker base because the stronger acid donates a proton to the stronger base. It follows that as a strong acid dissociates completely in water, the resulting base formed would be very weak. That is, strong acids have very weak conjugate bases. Strong acids like perchloric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid and sulfuric acid will give conjugate base ions ClO4 minus, Cl, Br minus, I minus, NO3 minus and HSO4 minus, which are much weaker bases than H2O. Similarly, a very strong base would give a very weak conjugate acid. On the other hand, a weak acid, say HA, is only partially dissociated in aqueous medium and thus the solution mainly contains undissociated HA molecules. Typical weak acids are nitrous acid, hydrofluoric acid and acetic acid. It should be noted that the weak acids have very strong conjugate bases, For example, NH2 minus, O minus 2 and H minus are very good proton acceptors and thus much stronger bases than H2O. Certain water-soluble organic compounds like phenolphthalein and bromothymol blue behave as weak acids and exhibit different colors in their acid and conjugate base forms. Such compounds are useful as indicators in acid-base titrations and finding out H plus ion concentration. Next, the ionization constant of water and its ionic product. Some substances like water are unique in their ability of acting both as an acid and a base. We have seen this in case of water in section 6.10.2. In presence of an acid Ha, it accepts a proton and acts as a base, while in the presence of a base B minus, it acts as an acid by donating a proton. In pure water, one H2O molecule donates proton and acts as an acid, and another water molecule accepts a proton and acts as a base at the same time. The following equilibrium exists. The dissociation constant is represented by the following. The concentration of water is omitted from the denominator as water is a pure liquid and its concentration remains constant. H2O is incorporated within the equilibrium constant to give a new constant K, which is called the ionic product of water. The concentration of H plus has been found out experimentally as 1.0 into 10 to the power minus 7 molar at 298 K. And as dissociation of water produces equal number of H plus and OH minus ions, the concentration of hydroxyl ions equals to 1.0 into 10 to the power minus 7 moles. Thus, the value of Kw at 298 K, the value of Kw is temperature dependent and it is an equilibrium constant. The density of pure water is 1000 gram per liter and its molar mass is 18.0 gram per moles. From this, the molarity of pure water can be given as H2O equals to 55.55 moles. Therefore, the ratio of dissociated water to that of undissociated water can be given as this. We can distinguish acidic, neutral and basic aqueous solutions by the relative values of the H3O plus and OH minus concentrations. Next, the pH scale. Hydronium ion concentration in molarity is more conveniently expressed on a logarithmic scale known as the pH scale. The pH of a solution is defined as a negative logarithm to base 10 of the activity of hydrogen ion. In dilute solutions, activity of hydrogen ion is equal in magnitude to molarity represented by H+. It should be noted that activity has no units and is defined as the following. From the definition of pH, the following can be written. Thus, an acidic solution of HCl will have a pH equals to 2. Similarly, a basic solution of NaOH having OH minus equals to 10 to the power minus 4 m and H3O plus equals to 10 to the power minus 10 m will have a pH equals to 10. At 25 degrees centigrade, pure water has a concentration of hydrogen ions. H plus equals to 10 to the power minus 7 m. Hence, the pH of pure water is given as pH equals to 7. Acidic solutions possess a concentration of hydrogen ions. H plus greater than 10 to the power minus 7 m. While basic solutions possess a concentration of hydrogen ions H plus less than 10 to the power minus 7 m. Thus, we can summarize that acidic solution has pH less than 7, basic solution pH greater than 7, neutral solution has pH equals to 7. Now, again consider the equation 6.28 at 298 K. Kw equals to 10 to the power minus 14. Taking negative logarithm on both sides of equation, we obtain pKw equals to 14. Note that although Kw may change with temperature, the variations in pH with temperature are so small that we often ignore it. pKw is a very important quantity for aqueous solutions and controls the relative concentrations of hydrogen and hydroxyl ions as their product is a constant. It should be noted that as the pH scale is logarithmic, a change in pH by just 1 unit also means change in H plus by a factor of 10. Similarly, when the hydrogen ion concentration changes by a factor of 100, the value of pH changes by 2 units. Now you can realize why the change in pH with temperature is often ignored. Measurement of pH of a solution is very essential as its value should be known when dealing with biological and cosmetic applications. The pH of a solution can be found roughly with the help of pH paper that has different color in solutions of different pH. Nowadays, pH paper is available with 4 strips on it. The different strips have different colors at the same pH. The pH in the range of 1 to 14 can be determined with an accuracy of 0.5 using pH meter, pH paper. For greater accuracy, pH meters are used. pH meter is a device that measures the pH dependent electrical potential of the test solution within 0.001 precision. pH meters of the size of a writing pen are now available in the market. The pH of some very common substances are given in table 6.5. Please check it. Table 6.5, the pH of some common substances, you can see it here. This is very important. Please remember all this. Next, ionization constants of weak acids. Consider a weak acid HX that is partially ionized in the aqueous solution. The equilibrium can be expressed by the given equation. Here C equals to initial concentration of the undissociated acid HX at time T equals to 0, alpha equals to extent up to which HX is ionized into ions. Using these notations, we can derive the equilibrium constant for the above discussed acid dissociation equilibrium. Ka is called the dissociation or ionization constant of acid HX. It can be represented alternatively in terms of molar concentrations as follows. At a given temperature T, Ka is a measure of the strength of the acid HX, that is, larger the value of Ka, the stronger is the acid. Ka is a dimensionless quantity with the understanding that the standard state concentration of all species is 1 m. The values of the ionization constants of some selected weak acids are given in table 6.6. This is a table, please check it out. The pH scale for the hydrogen ion concentration has been so useful that besides pKw it has been extended to other species and quantities. Thus we have pKa equals to minus log Ka. Knowing the ionization constant Ka of an acid and its initial concentrations, C, it is possible to calculate the equilibrium concentration of all species and also the degree of ionization of the acid and the pH of the solution. A general stepwise approach can be adopted to evaluate the pH of the weak electrolyte as follows. Step 1. The species present before dissociation are identified as Bronsted-Lowry acids or bases. Step 2. Balanced equations for all possible reactions, that is, with the species acting both as acid as well as base, are written. Step 3. The reaction with the higher Ka is identified as a primary reaction, whilst the other is a subsidiary reaction. Step 4. Enlist in a tabular form the following values for each of the species in the primary reaction: E, initial concentration C; B, change in concentration on proceeding to equilibrium in terms of alpha, degree of ionization; C, equilibrium concentration. Step 5. Substitute equilibrium concentrations into equilibrium constant equation for principal reaction and solve for alpha. Step 6. Calculate the concentration of species in principal reaction. Step 7. Calculate pH equals to minus log H3O plus. The above mentioned methodology has been elucidated in the following examples. Next, 6.11.4 Ionization of weak bases. The ionization of base MOH can be represented by the given equation. In a weak base, there is partial ionization of MOH into M plus and OH minus. The case is similar to that of acid dissociation equilibrium. The equilibrium constant for base ionization is called base ionization constant and is represented by Kb. It can be expressed in the terms of concentration in molarity of various species in equilibrium by the following equation. Alternatively, if C equals to initial concentration of base and alpha equals to degree of ionization of base, that is, the extent to which the base ionizes. When equilibrium is reached, the equilibrium constant can be written as follows. The values of the ionization constant of some selected weak bases Kb are given in table 6.7. This is table 6.7. Please check it out. Many organic compounds like amines are weak bases. Amines are derivatives of ammonia in which one or more hydrogen atoms are replaced by another group. For example, methylamine, codeine, quinine, and nicotine all behave as very weak bases due to their very small Kb. Ammonia produces OH- in aqueous solution. The pH scale for the dihydrogen ion concentration has been extended to get pKb equals to minus log Kb. Next, relation between Ka and Kb. As seen earlier in this chapter, Ka and Kb represent the strength of an acid and a base respectively. In case of a conjugate acid-base pair, they are related in a simple manner so that if one is known, the other can be deducted. Considering the example of NH4 plus and NH3, we see the following equations, where Ka represents the strength of NH4 plus as an acid and Kb represents the strength of NH3 as a base. It can be seen from the net reaction that the equilibrium constant is equal to the product of equilibrium constants Ka and Kb for the reactions added. Thus, this is the following equations. This can be extended to make a generalization. The equilibrium constant for a net reaction obtained after adding two or more reactions equals the product of the equilibrium constant for individual reactions. Similarly, in case of conjugate acid-base pair, knowing one, the other can be obtained. It should be noted that a strong acid will have a weak conjugate base and vice versa. Alternatively, the above expression can also be obtained by considering the base dissociation equilibrium reaction. As the concentration of water remains constant, it has been omitted from the denominator and incorporated within the dissociation constant. Then, multiplying and dividing the above expression by H plus, we get the following. It may be noted that if we take negative logarithm of both sides of the equation, then pK values of the conjugate acid and base are related to each other by the equation. Next, di and polybasic acids and di and polyester bases. Some of the acids like oxalic acid, sulfuric acid and phosphoric acids have more than one ionizable proton per molecule of the acid. Such acids are known as polybasic or polyprotic acids. The ionization reactions, for example, for a dibasic acid H2X are represented by the equations. And the corresponding equilibrium constants are given below. Please check all of them. Here, Ka1 and Ka2 are called the first and second ionization constants respectively of the acid H2X. Similarly, for tribasic acids like H3PO4, we have three ionization constants. The values of the ionization constant for some common polyprotic acids are given in table 6.8. Please check the table. It can be seen that higher order ionization constants are smaller than the lower order ionization constant of a polyprotic acid. The reason for this is that it is more difficult to remove a positively charged proton from a negative ion due to electrostatic forces. This can be seen in the case of removing a proton from the uncharged H2CO3 as compared from a negatively charged H3CO3-. Similarly, it is more difficult to remove a proton from a doubly charged HPO4- to anion as compared to H2PO4-. Polyprotic acid solutions contain a mixture of acids like H2A, HA- and A-2 in case of diprotic acid. H2A being a strong acid, the primary reaction involves the dissociation of H2A and H3O plus in the solution comes mainly from the first dissociation step. Factors affecting acid strength. Having discussed quantitatively the strengths of acids and bases, we come to a stage where we can calculate the pH of a given acid solution. But the curiosity arises about why should some acids be stronger than others? What factors are responsible for making them stronger? The answer lies in its being a complex phenomenon, but broadly speaking, we can say that the extent of dissociation of an acid depends on the strength and polarity of the HA bond. In general, when strength of HA bond decreases, that is the energy required to break the bond decreases, HA becomes a stronger acid. Also, when the HA bond becomes more polar, that is electronegativity difference between the atoms H and A increases and there is marked charge separation, cleavage of the bond becomes easier, thereby increasing the acidity. But it should be noted that while comparing elements in the same group of the periodic table, HA bond strength is a more important factor in determining acidity than its polar nature. As the size of A increases down the group, HA bond strength decreases and so the acid strength increases. For example, acids similarly H2S is stronger acid than H2O. But when we discuss elements in the same row of the periodic table, HA bond polarity becomes the deciding factor for determining the acid strength. As the electronegativity of A increases, the strength of acid also increases. Next, 6.11.8 Common ion effect in the ionization of acids and bases. Consider an example of acetic acid dissociation equilibrium represented as CH3COOH gives rise to H plus CH3COO minus, which is a reversible reaction. And next two reactions are also there, which are also reversible. HAC aqueous gives rise to H plus AC minus. Addition of acetate ions to an acetic acid solution results in decrease in the concentration of hydrogen ions, H plus. Also, if H plus ions are added from an external source, then the equilibrium moves in the direction of undissociated acetic acid, that is, in a direction of reducing the concentration of hydrogen ions H plus. This phenomenon is an example of common ion effect. It can be defined as a shift in equilibrium on adding a substance that provides more of an ionic species already present in the dissociation equilibrium. Thus, we can say that common ion effect is a phenomenon based on the Le Chatelier's principle discussed in section 6.8. In order to evaluate the pH of the solution resulting in addition of 0.05 m acetate ion to 0.05 m acetic acid solution, we shall consider the acetic acid dissociation equilibrium once again. HAC gives rise to H plus AC minus. So here is the derivation, please check it out. Overall, pH gives rise to 4.74. Next, 6.11.9 Hydrolysis of salts and the pH of their solutions. Salts formed by the reactions between acids and bases in different proportions undergo ionization in water. The cations or anions formed on ionization of salts either exist as hydrated ions in aqueous solutions or interact with water to reform corresponding acids or bases depending upon the nature of salts. The latter process of interaction between water and cations or anions or both of salts is called hydrolysis. The pH of the solution gets affected by this interaction. The cations of strong bases and anions of strong acids simply get hydrated but do not hydrolyze, and therefore the solutions of salts formed from strong acids and bases are neutral, that is, their pH is 7. However, the other category of salts do undergo hydrolysis. We now consider the hydrolysis of the salts of the following types. First one, salts of weak acid and strong base, example CH3COONA. Second one, salts of strong acid and weak base, that is NH4Cl. And third one is salts of weak acid and weak base, example CH3COONH4. In the first case, CH3COONA being a salt of weak acid, CH3COOH and strong base, NaOH gets completely ionized in aqueous solution. CH3COONA gives rise to CH3COO minus plus Na plus. Acetate ion thus formed undergoes hydrolysis in water to give acetic acid and OH minus ions. CH3COO minus plus H2O gives rise to CH3COOH plus OH minus. This is a reversible reaction. Acetic acid being a weak acid remains mainly unionized in solution. This results in increase of OH minus ion concentration in solution, making it alkaline. The pH of such a solution is more than 7. Similarly, NH4Cl formed from weak base NH4OH and strong acid HCl in water dissociates completely. NH4Cl gives rise to NH4 plus Cl minus. Ammonium ions undergo hydrolysis with water to form NH4OH and H plus ions. NH4 plus H2O gives rise to NH4OH plus H plus. This is a reversible reaction. Ammonium hydroxide is a weak base and therefore remains almost unionized in solution. This results in increase of H plus ion concentration in solution, making the solution acidic. Thus, the pH of NH4Cl solution in water is less than 7. Consider the hydrolysis of CH3COO NH4 salt formed from weak acid and weak base. The ions formed undergo hydrolysis as follows. CH3COO minus plus NH4 plus H2O gives rise to CH3COOH plus NH4OH. CH3COOH and NH4OH also remains into partially dissociated form. CH3COOH gives rise to CH3COO minus plus H plus. It is a reversible reaction. NH4OH gives rise to NH4 plus OH minus. This is reversible reaction. And the next one is H2O gives rise to H plus OH minus. This is also reversible reaction. Without going into detailed calculation, it can be said that degree of hydrolysis is independent of concentration of solution, and pH of such solutions is determined by their pK values. pH equals to 7 plus 1 by 2 pKa minus pKb, the equation 6.38. The pH of solution can be greater than 7 if the difference is positive, and it will be less than 7 if the difference is negative. Next, 6.12 buffer solutions. Many body fluids, example blood or urine, have definite pH, and any deviation in their pH indicates malfunctioning of the body. The control of pH is also very important in many chemical and biochemical processes. Many medical and cosmetic formulations require that these be kept and administered at a particular pH. The solutions which resist change in pH on dilution or with the addition of small amounts of acid or alkali are called buffer solutions. Buffer solutions of known pH can be prepared from the knowledge of pKa of the acid or pKb of base, and by controlling the ratio of the salt and acid or salt and base. A mixture of acetic acid and sodium acetate acts as buffer solution around pH 4.75, and a mixture of ammonium chloride and ammonium hydroxide acts as a buffer around pH 9.25. You will learn more about buffer solutions in higher classes. Next is 6.12.1 Designing buffer solutions. Knowledge of pKa, pKb and equilibrium constant help us to prepare the buffer solution of known pH. Let us see how we can do this. Preparation of acetic buffer. To prepare a buffer of acidic pH, we use weak acid and its salt formed with strong base. We develop the equation relating the pH, the equilibrium constant Ka of weak acid and the ratio of concentration of weak acid and its conjugate base. For the general case where the weak acid Ha ionizes in water, Ha plus H2O gives rise to H3O plus A minus, for which we can write the expression Ka equals to H3O plus A minus upon Ha. Rearranging the expression, we have H3O plus equals to Ka Ha upon A minus. Taking logarithm on both the sides and rearranging the terms, we get pKa equals to pH minus log A minus upon Ha. pH equals to pKa plus log A minus upon Ha, the equation 6.39. pH equals to pKa plus log conjugate base A minus upon acid Ha, the equation 6.40. The expression 6.40 is known as Henderson-Hasselbalch equation. The quantity A minus upon HA is the ratio of concentration of conjugate base, that is anion of the acid, and the acid present in the mixture. Since acid is a weak acid, it ionizes to a very little extent and concentration of HA is negligibly different from concentration of acid taken to form buffer. Also, most of the conjugate base A minus comes from the ionization of salt of the acid. Therefore, the concentration of conjugate base will be negligibly different from the concentration of salt. Thus, equation 6.40 takes the form pH equals to pKa plus log salt upon acid. In the equation 6.39, if the concentration of A minus is equal to the concentration of HA, then pH equals to pKa because value of log 1 is 0. Thus, if we take molar concentration of acid and salt, conjugate base, same, the pH of the buffer solution will be equal to the pKa of the acid. So, for preparing the buffer solution of the required pH, we select that acid whose pKa is close to the required pH. For acetic acid, pKa value is 4.76. Therefore, pH of the buffer solution formed by acetic acid and sodium acetate taken in equal molar concentration will be around 4.76. A similar analysis of a buffer made with a weak base and its conjugate acids leads to the result POH equals to pKb plus log conjugate acid BH plus upon base B. This is equation 6.41. pH of the buffer solution can be calculated by using the equation pH plus POH equals to 14. We know that pH plus POH equals to pKw and pKa plus pKb equals to pKw. On putting these values in equation 6.41, it takes the form as follows. pKw minus pH equals to pKw minus pKa plus log conjugate acid BH plus upon base B, or pH equals to pKa plus log conjugate acid BH plus upon base B, equation 6.42. If molar concentration of base and its conjugate acid cation is same, then pH of the buffer solution will be same as pKa for the base. pKa value for ammonium is 9.25. Therefore, a buffer of pH close to 9.25 can be obtained by taking ammonia solution and ammonium chloride solution of same molar concentration. For a buffer solution formed by ammonium chloride and ammonium hydroxide, equation 6.42 becomes pH equals to 9.25 plus log conjugate acid BH plus upon base B. pH of the buffer solution is not affected by dilution because ratio under the logarithmic term remains unchanged. Next, 6.13 solubility equilibria of sparingly soluble salts. We have already known that the solubility of ionic acids in water varies a great deal. Some of these, like calcium chloride, are so soluble that they are hygroscopic in nature and even absorb water vapor from atmosphere. Others, such as lithium fluoride, have so little solubility that they are commonly termed as insoluble. The solubility depends on a number of factors important among us, which are the lattice enthalpy of salt and the solvation enthalpy of the ions in a solution. For a salt to dissolve in a solvent, the strong forces of attraction between its ions, lattice enthalpy, must be overcome by the ion-solvent interactions. The solvation enthalpy of ions is referred to in terms of solvation, which is always negative. That is, energy is released in the process of solvation. The amount of solvation enthalpy depends on the nature of the solvent. In case of a non-polar covalent solvent, solvation enthalpy is small and hence not sufficient to overcome lattice enthalpy of the salt. Consequently, the salt does not dissolve in non-polar solvent. As a general rule, for a salt to be able to dissolve in a particular solvent, its solvation enthalpy must be greater than its lattice enthalpy so that the latter may be overcome by former. Each salt has its characteristic solubility which depends on temperature. We classify salts on the basis of their solubility in the following three categories. Category 1, soluble, solubility greater than 0.1 m. Category 2, slightly soluble, 0.01 m less than solubility less than 0.1 m. Category 3, sparingly soluble, solubility less than 0.01 m. We shall now consider the equilibrium between the sparingly soluble ionic salt and its saturated aqueous solution. Next, 6.13.1, solubility product constant. Let us now have a solid like barium sulfate in contact with its saturated aqueous solution. The equilibrium between the undissolved solid and the ions in a saturated solution can be represented by the equation BaSO4 gives rise to Ba plus 2 plus SO4 minus 2 in the presence of saturated solution in water. The equilibrium constant is given by the equation. Please check it out. For a pure solid substance, the concentration remains constant and we can write Ksp equals to KBaSO4 equals to Ba plus 2 SO4 minus 2. Equation 6.43. We call Ksp the solubility product constant or simply solubility product. The experimental value of Ksp in above equation at 298 K is 1.1 into 10 to the power of minus 10. This means that for solid barium sulfate in equilibrium with its saturated solution, the product of the concentrations of barium and sulfate ions is equal to its solubility product constant. The concentrations of the two ions will be equal to the molar solubility of the barium sulfate. If molar solubility is S, then 1.1 into 10 to the power of minus 10 equals to S square equals to 10 to S equals to 1.05 into 10 to the power of minus 5. Thus, molar solubility of barium sulfate will be equal to 1.05 into 10 to the power of minus 5 moles per liter. A salt may give on dissociation two or more than two anions and cations carrying different charges. For example, consider a salt like zirconium phosphate of molecular formula Zr plus 4 taken thrice, PO4 minus 3 taken 4 times. It dissociates into 3 zirconium cations of charge plus 4 and 4 phosphate anions of charge minus 3. If the molar solubility of zirconium phosphate is S, then it can be seen from the stoichiometry of the compound that, so here is the equations, please check it out. A solid salt of the general formula MP plus X, X, Y, Q minus with molar solubility S in equilibrium with its saturated solution may be represented by the equation. So here please check the equation, take a pause and check all the equations over here. The term Ksp in equation is given by QSP, section 6.6.2, when the concentration of one or more species is not the concentration under equilibrium. Obviously, under equilibrium conditions, Ksp equals to Qsp, but otherwise, it gives the direction of the processes of precipitation or dissolution. The solubility product constants of number of common salts at 298 K are given in table 6.9. So here is a table 6.9 showing the solubility product constants Ksp of some common ionic salts at 298 K. Next, 6.13.2 Common ion effect on solubility of ionic salts. It is expected from Le Chatelier's principle that if we increase the concentration of any one of the ions, it should combine with the ion of its opposite charge and some of the salt will be precipitated till once again Ksp equals to Qsp. Similarly, if the concentration of one of the ions is decreased, more salt will dissolve to increase the concentration of both the ions till once again Ksp equals to Qsp. This is applicable even to soluble salts like sodium chloride, except that due to higher concentration of the ions, we use their activities instead of their molarities in the expression for Qsp. Thus, if we take a saturated solution of sodium chloride and pass HCl gas through it, then sodium chloride is precipitated due to increased concentration of chloride ion available from the dissociation of HCl. Sodium chloride thus obtained is of very high purity, and we can get rid of impurities like sodium and magnesium sulfates. The common ion effect is also used for almost complete precipitation of a particular ion, as it is sparingly soluble salt with very low value of solubility product for gravimetric estimation. Thus, we can precipitate silver ion as silver chloride, ferric ion as its hydroxide, and barium ion as its sulfate for quantitative estimations. Next, the solubility of salts or weak acids like phosphates increases at lower pH. This is because at lower pH the concentration of the anion decreases due to its protonation. This in turn increases solubility of the salt so that Ksp equal to Qsp. We have to satisfy two equilibria simultaneously. So here is the derivation. Please check it out. Now again, taking inverse, we get the following, and it can be seen that F decreases as pH decreases. If S is the solubility of the salt at a given pH, then here is the equation 6.46. Thus, solubility S increases with increase in H plus or decrease in pH. Okay, so here is a summary of the lesson. Let's see. When the number of molecules leaving the liquid to vapor equals to the number of molecules returning to the liquid from vapor, equilibrium is said to be attained and is dynamic in nature. Equilibrium can be established for both physical and chemical processes, and at this stage, rate of forward and reverse reactions are equal. Equilibrium constant Kc is expressed as the concentration of products divided by reactants, each term raised to the stoichiometric coefficient. Equilibrium constant has constant value at a fixed temperature, and at this stage all the macroscopic properties such as concentration, pressure, etc. become constant. For a gaseous reaction, equilibrium constant is expressed as Kp and is written by replacing concentration terms by partial pressures in Kc expression. The direction of reaction can be predicted by reaction coefficient Qc, which is equal to Kc at equilibrium. Le Chatelier's principle states that the change in any factor such as temperature, pressure, concentration, etc. will cause the equilibrium to shift in such a direction so as to reduce or counteract the effect of the change. It can be used to study the effect of various factors such as temperature, concentration, pressure, catalyst, and inert gases on the direction of equilibrium, and to control the yield of products by controlling these factors. Catalyst does not affect the equilibrium composition of a reaction mixture but increases the rate of chemical reaction by making available a new lower energy pathway for conversion of reactants to products and vice versa. All substances that conduct electricity in aqueous solutions are called electrolytes. Acids, bases, and salts are electrolytes, and the conduction of electricity by their aqueous solutions is due to anions and cations produced by the dissociation or ionization of electrolytes in aqueous solution. The strong electrolytes are completely dissociated. In weak electrolytes, there is equilibrium between the ions and the unionized electrolyte molecules. According to Arrhenius, acids give hydrogen ions while bases produce hydroxyl ions in their aqueous solutions. Bronsted-Lowry, on the other hand, defined an acid as a proton donor and a base as a proton acceptor. When a Bronsted-Lowry acid reacts with a base, it produces its conjugate base and a conjugate acid corresponding to the base with which it reacts. Thus, a conjugate pair of acid-base differs only by one proton. Lewis further generalized the definition of an acid as an electron pair acceptor and a base as an electron pair donor. The expressions for ionization constants of weak acids and weak bases are developed using Arrhenius definition. The degree of ionization and its dependence on concentration and common ion are discussed. The pH scale for the hydrogen ion concentration has been introduced and extended to other quantities. The ionization of water has been considered, and we note that the equation pH plus POH equals to pKW is always satisfied. The salts of strong acid and weak base, weak acid and strong base, and weak acid and weak base undergo hydrolysis in aqueous solution. The definition of buffered solutions and their importance are discussed briefly. The solubility equilibrium of sparingly soluble salts is discussed, and the equilibrium constant is introduced as solubility product constant Ksp. Its relationship with solubility of the salt is established. The conditions of precipitation of the salt from their solutions or their dissolutions in water are worked out. The role of common ion and the solubility of sparingly soluble salts is also discussed. So here with this we are done with the lesson. If you like my audiobook, please share it to your friends, like and subscribe.